Okay, we're about to get started with the last part for homework 2, part D, and this is kind of building off of the previous part, part C. We're going to take the heat diffusion equation that we derived in part C1, take it as an algebraic equation via Crank-Nicolson differencing, and basically we're going to show why we want to use this, and it's because that we can basically have a larger time step, and then certain values of R aren't going to make our system unstable or diverge, and it gives us a lot more moving room and freedom. So I'm going to get into the derivation, and then I'll code up an example to show what I just explained. As I was saying, the first thing that we're going to do is express this heat diffusion equation from part C1 as an algebraic equation via Crank-Nicolson differencing. Our previous method was an explicit method in which we were just taking our current spatial node and then looking what would happen in the future. But now what we want to do is this implicit method, the Crank-Nicolson differencing. So this is going to determine the next state by involving both the current and future states, not just the current state. And this results in a higher stability in general, and a higher accuracy, and then also a higher stability when using larger time steps. We're not going to be restricted to that R value of 1/2, and I'll show why, but let's get started on this. Previously, this is the equation that we used just as a reference to kind of look at how the next one is different. So in a similar way, we're going to have ti to the n plus 1 minus ti to the n over the time step. This time we're looking at the current time step and the previous time step when we're calculating the future time step, if that makes sense. So we have our thermal diffusivity like we had previously, and we're going to divide this by 2 because we're taking an average. Before I go any further, I did want to touch on the previous video. When I edited back through it, I did try to highlight my errors, but I would like to quickly review that because it's kind of similar to what we're doing now. So I just want to reiterate negative, so I minus 1, minus 2, etc. is to the left, and I plus 1, plus 2, etc. is to the right. And then I think I rewrote that here. And here's another thing, is I accidentally put a negative there. It should be positive. I went back through and fixed it just for my notes for myself. But again, that should all be positive. I did fix it in the video when I got to this point, but I just neglected to explain what had happened there. And now we can move on with what we're actually doing for this video. So we have the temperature node to the right, I plus 1. And we're doing this for the next spatial node. So remember that I is the spatial node, n is the time step, delta x is the spatial step size, delta t is the time step size. Like we did previously, subtract the 2t, the temperature at our current node, but at the our temperature at the current spatial node, but at the next time step this time, and add the temperature at the I-1, which is the left node, the node to the left of I. And this is all going to be over the spatial step delta x squared. And as I was saying, we're not just looking at the current node, we're looking at the future node, which is why I did this n+1 first, to make sure I didn't forget that. But we also need to add our current node. As you can see, it looks a bit similar to what we had before, except we have these terms now. That is like the main difference. And as I said, this is taking the average of n and n+1. So looking at where we are currently and where we are in the future. And then now I want to get it in a similar form to this guy. So I'm going to have ti to the n+1. I'm going to multiply this delta t to the other side. And take out that delta x squared, since it's in the denominator of each of those on the right-hand side. I'm also going to go ahead and add the ti to the n. As you can see, this is our r value right here. This was our previous r value. So it's the same except divided by 2 because we are taking the average. And then it's just the rest of those terms that I have above. And that right there is our final equation from the Crank-Nicolson method. Now we want to use the von Neumann stability analysis to show that the Crank-Nicolson differencing scheme is stable regardless of the choice for r. Notice again that is divided by 2 due to taking the average of the two, taking the average of the current time step and the next time step. So I quickly tried to simplify what I circled in blue up there. And it is now here. I just replaced this thermal diffusivity, delta times delta t over 2 times delta x squared with r, so now r is in there. And this side has all the n+1 terms, and this side has all of the n terms. AKA, this is the, or I guess I could say next time step. And this is the current time step. When we kind of display this as a matrix, we get what is called a sparse matrix. And this is because we have repeating diagonals of this 1 plus 2r, as well as repeating diagonals. This one should be an r, a negative r. Hang on. So we have these repeating diagonals, as I was saying, right there, of the 1 plus 2r. We also have repeating diagonals of the negative r, and this would continue. I just did not write the entire matrix, but We also have those negative r's. There's 2 of them. And when we multiply them, we basically get our known values. And it's called a sparse matrix because other than the diagonals of 1 plus 2r and negative r, everything else is all zeros. So this would actually be all zeros until it reaches the end. Basically, as we know, this 1 plus 2r is at the current node, and the negative r is at either the node to the left or to the right, and that helps us simultaneously solve for all of these values at once. And now what we really wanted to do was show the stability regardless of the choice of r. From the previous homework, we're going to do something very similar, except now we have more terms. So, like I said I'll choose a different color. Like I said with this right here, this time, I'll do it over here. We can take the ratio of ti to the n plus 1 over ti to the n. And this is going to be equal to 1 minus the 2r plus r times e to the I, don't forget the k, delta x. And then the other side, e to the negative I k delta x. This one is 1 plus 2r minus r times the same values above. And just to, I guess, remind you where these values come from, I'm getting it from here, just factoring out the ti to the n plus 1, and then this is how we deal with the right and left nodes, rather than having I plus 1 or I minus 1. And then we know that we can write this in terms of cosine. So I'll rewrite that out with 1 minus 2r still, 1 plus 2r still. But up here we have plus 2r cosine. Make sure I have that k in there this time. Delta x. Same thing on the bottom, but it's negative. And so this is what we end up with. Now what we notice is that no matter what, this ratio is bound between negative 1 and positive 1. For example, if our r was 10, we would have 1 minus 20 plus 20 cosine k delta x, 1 plus 20 minus 20 cosine k delta x. These are always going to be equal to each other. For these values will always be equal to each other. So for the case of cosine k delta x being 1, we would have 1 minus 20 plus 20 divided by 1 plus 20 minus 20, which that is 1. So basically this ratio, the ratio of this cannot be less than negative 1 or greater than positive 1, which would cause instability. And because it can't exceed those, we know that we can use any value of r. rather than being stuck with this 1/2. Because no matter what r we choose, because of the way this is set up, you cannot exceed those values, when before we did not have a ratio like that. So we are doing this third part. We're going to simulate similar to what we did in part C, but we've clarified a few more values and specified some other things. So the bar is 50 centimeters long. The thermal diffusivity and the time step are given to us, so we are not setting that ourselves. Last time we just chose a value of r. And this is, again, a uniform bar, initially at 20 degrees Celsius, and then its ends are raised and maintained to 50 and 80 degrees Celsius. Note that that is different than what we did in part C. So I'm going to discretize that into 1 centimeter sections and then solve it. Solve the equations from the equation I created in part D1 using this time step of 0.1 seconds for 10,000 time steps, and I'm going to plot this in 20 time step intervals. As always, I have this import up here. Then I want to start off with what was defined. So our alpha, our thermal diffusivity is 1 times 10 to the -4th meters squared per second. And we put it in exactly like that. We also define our dt as being 0.01 seconds. Or sorry, 0.1 seconds. And our dx is 1 centimeter, but this is in meters, so we are going to do 0.01. That's where I was taking that number from. And of course we have to define our r, so that was alpha times dt divided by dx squared. There should be also a 2 here. And then I can actually run this and get a value for r. So right now our r value is 0.05, just to take note of that. Later on we will change it up for a time step of 10 seconds, and as you can see that gives us an r value of 5, but for now we are doing 0.1 seconds. So since that's going to be in 1 centimeter sections, we have 50 different sections. The temperature at the start, similar to part C, starts at 20 degrees Celsius across the entire bar. The left side of the bar we're going to set to 50 degrees Celsius, and the right side we're going to set that as I think it was 80 degrees Celsius. And now we're about to put in the sparse matrix that I was talking about. Alright, as I was saying, we're going to go ahead and fill out our matrix that I talked about. So first we have a diagonal of -r. We use this n-2 because there are n-2 interior nodes being solved next to the current node. So we have that, We also have this that it wants me to do is correct, I believe. We had our 1 plus 2r diagonal, and then we also had another negative r diagonal. And then for plotting the x-axis, I'm going to do it like this right here. Our usual make sub plots. We're going to add a scatter. X is that IDX that I defined above. Y is the temperature. We can do lines as our mode. And again, I should have specified this is for temperature equal to 0. So this will be before anything has changed, 50, 80 on the ends, and then 20 in between. And now we need to do our for loop to get the 10,000 time steps. So for n in range 10,000. So now we're doing the known side, which was the right-hand side of our vector, in which we know what is happening at a certain time, and we're going to call that b. That should be 1 minus 2 times r times the temperature at any moment plus r times the temperature r times the other temperature, or that should be 2. And then we can say b at the index of 0 is equal to this plus equals is basically saying we're taking this b at an index of 0 and we're adding r times t at the index of 0. So this is for the left boundary, and we need to do the right boundary. So a similar thing there. And then this is the right boundary. And then now we want to solve for those unknown interior temperatures. So we go from the second node until the penultimate node, so that we're not messing with the first or like the left or right hand side, which are supposed to stay at 50 and 80 degrees respectively. Okay, linear algebra dot solve banded. And then we're using the first matrix that we had, and then also matrix B, we just left that as B. This is the temperature at time n plus 1. And then similar to what we did in part C, we don't want to plot every single line. So we're going to use this modulus and add a scatter like that, only if the remainder is true right here. And this name is actually n plus 1. I'm going to update the layout like I typically do. One-dimensional heat diffusion, Crank-Nicolson this time. The x-axis title is going to be node index. y-axis title is the temperature in degrees Celsius. The legend title is going to be time step, so that we can keep track of what time step we're on. Height, width, I think I usually do, that's fine. And my usual template. Right there. And then we'll do fig show, and hopefully it shows up correctly. Okay, looks like I meant to put a colon there, not a semicolon. Hopefully that's the only big issue. Yeah, I did flip what I usually do for the height and width, so hang on. Alright, I just edited the width a little bit more, and now we can see it pretty well. We do have quite a bit of lines, so if you wanted to, you could change that modulus so that we don't have quite as many lines, but it is pretty similar to part C, except we just changed the temperatures on each side of the bar to 50 and 80 degrees. And this time we're calculating it with this implicit method from our Crank-Nicolson calculations. So what we want to do now is repeat D3, but for a time step of 10 seconds. So R will be 5, and show that while at early times it can be inaccurate, the numerical solution remains stable, unlike what we saw in part C. So dt is 10, and that should make R 5. I'll run the whole thing. And remember, in part C we did this basically same thing but with an explicit method, and our R value had to be either equal to or less than or equal to 1/2. So yes, it looks very wonky, and here is what my professor was saying about the earlier time steps. At this first time step, we see this odd increase here, which wouldn't happen, but other than that, most of the other time steps are fairly reliable. And when we tried to do this with the, when we did the explicit method in part C, we just had insane oscillations that we could not read whatsoever. Now I'm setting R as 1.0 just to see what that kind of looks like, if we can find a nice middle ground where we get the best of both worlds. Yeah, so this still looks really good. So this is kind of the best of both worlds, where we don't really have those errors at the beginning, but we were able to increase our time step. With R equal to 5, it can be inaccurate towards the start, but we don't have those crazy oscillations that we had in part C that, like I said, made it completely unreadable and unusable. The graph was not usable. So that was the last part for homework 2 for process dynamics and controls. Pretty soon homework 3 is going to be out, but yeah, thank you for watching, and stay tuned for the next homework.